In this part of the lecture, I wanted to remind you that we are in the course of organic reduction and in the lesson about soil fertility management, as you see in the slide. I am Professor Devairi Dulia. The last soil property is listed in the physical properties of the soil. There is bulk density. Bulk density of the soil is the proportion of the weight of the soil relative to its volume. It is expressed as a unit of weight per volume and is commonly measured in units of grams per cubic centimeters. Bulk density, in fact, is very linked to the structure that we spoke before and to the pores. So, when the bulk density is high, this means that we have less pore volumes, and in the contrary, when the bulk density is lower, this means that we have a bigger space, a bigger volume of the pore spaces. So bulk density is an indicator of the amount of the pore space available within the individual soil horizons. It is inversely proportional to the pore space. So the pore space is equal to 1 minus bulk density to particle density. The addition of even a small percentage of organic soil material to a mineral soil can decrease the bulk density of the soil. First of all, because the soil organic material is lighter than the minerals, and on the other side, in case of structural soil, a good space, as I explained before, it is occupied by the pores and the air and not by the particles of the soil. Okay, now in this slide we start to speak about soil chemical properties. The previous slide was the last slide or the last property included in the list of soil physical properties, and it was bulk density. One of the soil chemical properties, an important soil chemical properties, is cation exchange capacity. The cation exchange capacity of the soil is the amount of cations in a particular sample of soil can hold in an exchangeable form. Cations leaving the exchange sites enter the soil solution, where they can be taken up by plants, react with other soil constituents, or be carried away with drainage water. The greater the clay and organic matter content, the greater the cation exchange capacity. Though different types of clay, minerals, and organic matter can vary in cation exchange capacity. Speaking still about cation exchange capacity, it is important to explain here that some plant nutrients and metals exist as positively charged ions or cations in the soil environment. Among the more common cations found in soil are hydrogen, aluminium, calcium, magnesium, and potassium. Most of the heavy metals also exist as cations in the soil environment. On the other side, clay and organic matter particles are predominantly negatively charged. They are anions. And being anions or having negative charge, they have the ability to hold cations, and these help to protect cations from being leached or washed away. So, I wanted to stress here that most of the cations that are minerals from where the plants are, um, how to say, taking nutrients, they are positive and they are not leached away by water exactly because they are kept on the soil from the combination of their positive charge with negative charge of the clay and the organic matter particles that are in the soil. But these cations will not stay always linked to the negative anions or to the negative ions of the clay and organic matter in the soil. The so-called absorbed cations are subject to the replacement, so they can be replaced by other cations in a rapid, reversible process. And this process of replacement of one cation from another cation is called cation exchange. Let's see here a list of elements. Here you have a list of some elements that can be found in the soil and that are important for the soil and for the plants. So we have here a list of essential elements, and I invite you to have a look, to try to memorize them. There is a list of elements that are toxic to plants like lithium, beryllium, lead, aluminium, cadmium, mercury, and lead. There are some other elements that can be natural, neglectable. The elements that are minerals that can be taken from the plants, they are grouped at least into big groups: macro elements and micro elements. Macro elements are the most important nutrients of the plants or for the plants. The macro elements are calcium, magnesium, potassium, sulfur, phosphate, nitrogen, and sodium. They occur naturally in the soil to some extent and can be supplemented with fertilizer, manure, and compost. Legumes and some microorganisms in the soil are able to be nitrogen from the atmosphere. Speaking about microelements. Microelements are called to trace elements. They are nutrients that plants need in small doses. The trace elements are boron, copper, manganese, cobalt, silicon, zinc, iron, and molybdenum. Signs of shortage occur when the loss of trace elements through the crops is not compensated adequately with supplements by means of fertilizer, manure, or compost, or when the availability of certain elements is limited by the pH or mineral imbalance in the soil. It is difficult to solve a lack of trace elements in the plant at source, as many shortages are the result of a shortage or surplus of another mineral in the soil. Crop analysis can help to trace an acute shortage and to solve it at plant level. Soil analysis provides insight into the total mineral balance, which tells you where shortages can be expected, which can then be solved. Another chemical property of the soil, there is salinity. Salinity is related to the salt content in the soil. The salt level is the sum of all the mineral salts that are present in the soil. They can originate from the soil itself, from the fertilizer, from organic manure, and in coastal areas from salt marshes or tidal marshes. When the salt levels in the soil are higher than in the cells of the plant roots, the moisture is drawn from the roots, and the fine-haired roots die off. Over time, this impedes the moisture and nutrients absorption by the plant and causes reduced growth, but not only the reduced growth. If it is a very high content of the soil, we can have death of the plant. However, the plants are different. They vary in the extent to which they tolerate salt and the salt levels at which they can still provide a good yield. Some crops grow well in salty soils. The causes of salinization of soils are irrigation with underground water or salty water sources and fertilizers. So this means the fertilizers plays a role in the salinity of the soil too.